Okay, so this is going to be a lecture about ideals and special types of elements in a ring. So one special type of element that we would like to consider is, as we've seen in the last lecture, there's special importance to elements, non-zero elements that have a multiplicative inverse. We will give those a name. Those will be called units. Regarding ideals, we want to have a generalization of some of the things that we did for groups, like having quotient groups, kernels, isomorphism theorems. We want to have all of this for rings, and we can have that just as soon as we have the right generalization of normal subgroup, and that will be the notion of an ideal. Okay. First, we need to generalize homomorphism. So this is rather straightforward. So a homomorphism between two rings R, S is a map phi from R to S such that first we want it to be a homomorphism for the underlying additive abelian groups, because remember that R and S are, after all, also abelian groups. So that will say that phi of A plus B is equal to phi of A plus phi of B for all A, B, and R. Secondly, we want to say that phi is also multiplicative for its multiplication, so that if it was also a group, if R and S were also groups under multiplication, or that can't happen, but if they're groups under multiplication when we remove 0 from them, so that will happen, for example, if they are both fields or both division rings, then in that setting we would want that the map between those groups be a group homomorphism. And the way to say that is to require that phi of A times B is phi of A times phi of B, again for all A and B in R. So phi of a sum is the sum of phi of the elements. Phi of a product is the product of phi of the elements. Okay, now from here on I want to look at ideals. I want to make an assumption. So assume from now on that R is commutative. And we already said that we are also assuming that it has a 1, but we continue to assume this. Okay? So really the study of non-commutative rings is something much more complicated that is interesting to consider in another course. So let's restrict attention to R commutative. So then we have the following definition. An ideal I in R is an additive subgroup. So that is, it's a subgroup of R with the plus operation. And now we have to say something also about the multiplication, such that RA is in I for all A in I and R in R. So this might seem strange at first, right? Because I'm allowing to multiply by all elements of R on the left. Notice that I've assumed that R is commutative. So at this point, this also means that we are allowed to multiply by all elements of R on the right. In non-commutative rings, one then separates between left, right ideals and two-sided ideals. But why is this a natural thing to do? Because this is exactly what gives you the ability of forming a quotient. This is exactly the, so remark, ideal is the right generalization of normal subgroup from groups to commutative rings. Okay? To see this, you have to try to define a ring structure on the quotient by an additive structure, and you will see that for that to make sense, you exactly need this condition to be satisfied. Another thing that we can see is if phi is a homomorphism between two rings, like here, then we have its kernel as with groups. It's the set of A and R such that phi of A is equal to 0. And it's easy to see that the kernel of phi is an ideal. Because if I look at phi of R times A, well, this is phi of R times phi of A. And then now I'm like over here, I have R and A in the ideal. Now because A is so A is in the ideal, and my ideal here is the kernel of phi. Because A is in the kernel, this phi of A is equal to 0. So this is phi of R times 0, which is equal to 0, which implies that RA is again in the kernel of phi, which shows that the kernel of phi has this ideal property. Okay? So this is a good one sign that we have made the right choice. So now another reason is that, as I said, we want to have quotients and the isomorphism theorems. So if I is an ideal in R, we have a quotient ring R mod I, and again, the elements here are going to be cosets. Now we write them additively. So this is the set of all R plus I with R in R. So this R plus I, this signifies the coset of I in R represented by the element little r in big R. And ideals and quotient rings satisfy the three isomorphism theorems. So let me just, because this part, once we did, the key thing was to come up with a notion of ideal. Once we have that notion, now the isomorphism theorems go through exactly in the same way as for groups. So let me just tell you how the first one goes. So we have, for example, first iso theorem. So this says, assume phi from R to S is a ring homomorphism, then phi factors through phi bar in the following diagram, remember we had one of these diagrams for groups, so I have R projecting by the projection to R mod I. This sends an element S in R to its coset S plus I. And then I continue by this map phi bar, whose existence I am asserting onto S, like this. So this is phi, and then I'm saying that phi bar is injective. So phi bar is an isomorphism onto its image. So I have R mod I mapping isomorphically onto the image of phi bar, which is also the image of phi. And as in the case of groups, in particular, if phi to begin with was surjective, if phi is surjective, then R mod I, well then R mod I is isomorphic to the image, which is all of S, so R mod I is isomorphic to S. Okay. Okay, so actually let's go back for a second and let me quickly justify for you why the notion of an ideal that I wrote down is actually the correct one. So if you think about it, what we want to do to define the quotient so we need multiplication of cosets. So it would mean I would have R plus I and S plus I. I'd need to multiply them together. Now, the natural thing to want this to be is to want this product to be the coset represented by the product R times S. So we would want this to be Rs plus I. But when we actually multiply this out, what comes out? What comes out is Rs plus R times I plus I times S, but I times S is S times I, because I'm assuming my ring is commutative, plus I squared. Now this I squared is harmless. I squared is contained in I. If we assume I closed under multiplication, which is a weaker condition than the ideal condition, this would imply that i.e. I is a subring. This would imply that I is a subring. But my point is, why would this not be enough? Because then adding this doesn't change anything, but this is contained in I, but we have Ri and Si. We want to get plus I. Here, if we just assume I is closed under multiplication, we are potentially getting something bigger. So we need Ri equal Si equals I. Then we're okay. So this justifies the definition of an ideal. Okay. Let's see some examples of an ideal, of ideals. So just like the identity is a trivial subgroup of every group, the zero ideal is a trivial example. in any ring of an ideal. And we can also take R itself is an ideal in R that's corresponding to the identity in the whole group itself. More interesting example is I can take NZ in Z. So what is NZ? So this is for an integer NZ. This is all the multiples of n. So this is all the k times n with k in Z. So for example, n equals 2, 2z, this is the even integers. Okay? And we see that these are ideals. The map from Z to Z mod NZ that takes an element n, not n, k to k to its residue class mod n, in other words, reduction modulo n. This is a homomorphism of rings, and let me call this pi, and the kernel of pi is the ideal NZ. And then this is a surjective homomorphism. We know that every residue class is represented by an integer. And then by the first isomorphism theorem, we have that Z modulo NZ is isomorphic to Z modulo NZ, where here I mean the quotient of the ring Z by the ideal NZ. Here I mean the ring that we have defined Z mod NZ. But this is, of course, the reason for the notation Z mod NZ. Okay? And this is also the reason why any textbook in which you read of other notations like Zn or things like this is absolutely no good. This represents very well that what this ring is the ring of integers modulo the ideal of multiples of n.